Yes, welcome people. We are going to continue with our interactions and effects. And now I'm going to talk about dark and chaotic interactions. Dark and chaotic effects. Interactions. The word dark is very popular nowadays with dark matter, dark energy, dark anything you like. So this is also interesting to have that definition in the dim model. Okay, so now, even if something is not realizing, I have a process A not realizing in an interval I. And there is an interaction of A and B, which realizes to something after both have realized, so after I. Well, you will see, and it's very easy, the shifting of these intervals, which is not available in the classical theory, but we define existing in a proper way. We have to suffer this shifting of intervals. So that is explaining a lot of new phenomena. And of course, when you think about just the observation of these things, you will probably never observe them, because usually its existence intervals are much smaller than observation intervals. So it is below the Planck unit interval, if you want to define that. So these small differences are sort of invisible, but they are important for certain effects, because they have effects. That's what I'm now trying to explain. And so when there is an effect, then there is the dark effect of the short string. Short string for a t to, let's say, a t1, or t1, so t1, the interval t1, smaller than the interval r, smaller but different. There's a shorter interval. I can look at some subset of dark effect, so C in A, and like I said before, but I erased it, it was in the foregoing lecture. Dark effect of this is a dark effect because A does not exist and the effect is already there. So dark effect, A not existing, yet it will exist later probably, later. But the effect, as I defined it the other time, but the effect exists. Now there's no way that you can find that this effect is caused by A, because A does not exist. Even if it exists, you have to observe, and then it's many states of the universe further. But that's not so important here. But this is certainly clear that if something is not existing, you can not see it. And if you cannot see it, you cannot see it, but you can see the effect. The effect is existing, and if you observe, you will see that maybe even before this exists, this is possible. Because the existence intervals for some things are very long, and for some others can be very quick. We don't know this. I didn't put any rule there because I have no way of finding what kind of reality is there. I mean, I have the feeling that there can be even infinite, well, I say infinite, I mean, in all the remaining time in the future. So something, a process starting at t, let's say. So okay, here is the interval t, and then it goes on forever, all t prime, and so for all t prime bigger than t in the future. And that is the existence interval. All. So in fact, I could write this as t infinity. But be careful, infinity is not in time. It means all the remaining time. So an existence interval like that, it can be, why not? In fact, in the more philosophical discussions I have sometimes, and also maybe at the end of this series, I will do some of that. You could in fact argue that the soul is an abstract thing in the definitions for me, but it could exist at infinity, which is for the religious people very acceptable because they think, oh, it's in heaven. But it's just the fact that this interval can be all the time. If time is finite, okay, then it's finite, but let's say that the assumption is time is not finite. We don't know if there is an end of time, so be it, there was a beginning. There may be no beginning, there may be no end, we don't know. There are theories, but there are theories, so I assume this is possible. Okay, so if you have such a thing interacting with kind of never really existing, then or not existing in a very long period after the things all exist, and this is still not existing. It's not necessary to be infinite, but long enough to be away from everything else. Then I call that a chaotic interaction. Chaotic interactions are worse. They will absolutely never be discovered and never be understood, I guess. But they can be there and they can be very important. So, in fact, the chaotic interactions seem, in my opinion, if you write down the definition exactly, which I don't do, I just say it like this, not existing. Then you can imagine that it has specific value for infinite process. I have never said the process are finite. They can go on forever. Of course, they may vanish sometimes to go to the empty set. The AT goes to the empty set, it's gone, it stops. The empty set only goes to the empty set in the connections. So if it stops, it stops. If it doesn't stop, it goes as long as time goes. And that can be infinite. So for that reason, some processes which do not realize in the finite area, let's say, but have a meaning after all time. That is very possible. No, it is even plausible, I think. So that is something one has to look at, perhaps. They are never observable, they will never even existing, except at the end of time, let's say, looking at the finished universe. So there is some importance. In fact, they may be the most important. They may be steering, because they can interact with everything all the time. They can have all these effects. It is not because it doesn't exist that it cannot have effect on the contrary. It has all these dark effects. And these dark effects may be perhaps the most important. It's not that we cannot observe them, that they are not important in this evolution of the universe. They can be the most important. They have probably the most effects also. So if they are there, they are most important, I would say. Okay, so that is an interaction, dark effect. Dark matter can be a dark effect. It can also be matter in a non-observable place. So there are different possibilities for dark matter and dark energy to be in the void. But in any sense, for our model, for example, dark matter is a process, and it's on a short string. It is not realized. If it's realized, it can also be an existing thing which is unobservable, because it's no proof that everything existing can be observed. But usually one assumes that, let's say, but of course without proof and even without evidence. I mean, you can never look at something which is not observed and say, oh, okay, this is an example. Okay, good. So that's the story about the effect, dark effect. Okay, so I will now go to an important section, a new section, which is the breaking down of causality. I have said it before, I think, but now let's look at it a little bit closer. The organic causality. All our physics and all our reasoning is built on the question why, cause and consequence. We want to know what causes something, otherwise we are left in a swamp. We don't like to be in the swamp. So I will now talk about organic causality. I'm not sure if I have it. I want to finish this in one series, so perhaps I will do some introduction before this and then do the organic causality in the next mini set. But first I will then talk about the learning process. Because, well, this is of course important for humans. We learn very well, it seems, and a lot. But it's true for all organisms, and we don't know how they learn, but they sure learn too. They learn how to behave in their environment and so on. So they also have learning processes. And so what is it? Well, I have ingredients. For example, I have some materials in the river, and I have a relation. A relation is given by a set of pairs, ordered pairs. A, B, for example. A first and B second. And then usually, because it's ordered, you can write it as A arrow B. It's not an implication. Implication are very good examples, of course. But it's giving you the order, A before B. So, examples, well, learning, studying a proof of a theorem. I used in the course of didactics, I used what I'm saying about this learning process. We published some papers together with people in psychology from Austria and China. But for me it was important in the didactics of mathematics to apply this to, for example, a proof of a theorem where every statement was an ingredient and the relation between the statement was the logical relation. And it has a diagram of partial order and so on. So this is a good example. Example also, the pollution of a river. Well, there are thousands of examples. It's just writing a music, writing an opera, for example. Pollution of the river, so on. When I wrote about this publication, that it was used by the people in the other part of the university. There was some project with the petrochemical industry near the river. Because the safety of the, well, I can write it, safety of industrial constructions. So there is some applications of this theory that I made for the learning process. So when you have like a written course, you view this as the learning object, the study object. Then you view the ingredients of the course, which are the things that you learn about, the objects that you can easily find, the important things. And the relation between them is then usually the relation can be a logical implication. Relation is either a logical implication or a causality. Both of these are partial orders. So, if you want to catch both logical implications and causality, you have to make the relation a partial order relation. That's the most interesting case. If it's not partial orders, they also have this Hasse diagram of the logical structure. So they have some structure like implications. For example, let me write in small letters: A, B, C, D, C, E, C. There are no arrows going back. Partial order is anti-symmetric. So, and you go on like that, and there's a Hasse diagram. So this is the Hasse diagram. And this is the logical structure of the thing that is partially ordered, the ordered structure. Okay, so the students in math did this for theorems and so on, they made the diagram. And then when you want to have a didactical application, you say, oh, the students have to know this diagram to understand the proof. And when you read the diagram, if you read the proof or you tell the proof to the students, you talk about it or you write about it, whatever you do about it, you always take a linear order because you order it in time, chronologically. You say first this and then that, but then you have a choice to go here or here. And maybe there's some interactions here. There's a complicated diagram. So when you present a linear formation, linear form of that in time, then the structure of the proof is not clear. So the result of this idea, one of the results is to say, well, the students have to know this structure before understanding the proof, before giving the proof. You just say, okay, look at this proof, look at this and that, and there is the structure. And now give the proof. And then you will see that you first go, for example, to A D and DC or A something else, and you follow a path, which is not the diagram. So that is this gives you the uncertainty principle of learning. And I believe, and I'm sure in fact, but what does it mean to be sure? I doubt, but I look like I'm sure, that this is the main difficulty for students to understand the logic of the proof. And this is very clear in mathematics, but it's true in all learning processes. And there's another aspect. For example, if I want to learn, observation is also a learning process, so we're going to use that. If I observe something like an apple, I can see the shape. Okay. Apple. What is this, 2 P's and an L? Or 2 L's? Okay. Just like that. I don't know. Anyway, you observe an apple, and you have the shape. This is very easy to see, everybody sees it, and almost only this observation or this fact or this thing that you see is enough to know that it's an apple for most people. You can be very wrong, but not so many objects look exactly like an apple, so this is not so bad as a first description. But maybe you want to know much more, so then you can wonder about some chemical structure. The taste, the molecules, which is related to the chemical. Anyway, you can do the genetic structure. So when you learn a certain thing in a process, you can refine the process. So you refine by splitting an ingredient in aspects. So instead of looking at the ingredients, you look at some other things which make up the ingredients. And then you have a finer analysis of the problem. And this is also what physics does. The better the telescopes, the finer, the more you see, the more the theory becomes more and more precise. So you have this process here, A goes to B, goes to C, and then you replace A by a set of A1, AN, B by B1, BK, C by C1, CL, and these arrows are replaced by arrows in these directions. well, that's only one arrow leaving. So you have this diagram is the refinement of this sort of primitive learning process. This is a more advanced learning process. What is interesting for all the applications I will eventually mention in this series of lectures is that there can be counter-intuitive arrows, like here. Oh, columns are not really shown on this blackboard, but it doesn't matter. It goes from here to here. The arrow goes in this way, but here you have arrows going in the wrong way, anti-causal. For if the relation is causal here or logic, then this is anti-causal or anti-logic. So, but this happens a lot. When you analyze the smaller ingredients, not necessarily the relations are all in the same direction. And so this kind of anti-causal, anti-causal, anti-logic is where creativity is. Because just to realize that something is not causal, but even anti-causal, needs kind of open mind. You have to allow you to think like that. People usually don't do that. If they see something which goes against their principles, they dismiss it. They don't accept it. But this is the important place for creativity. So creative people are broad-minded, usually. At least in this sense, let's say. Not necessarily in others. But okay, so this is creativity. And it requires more than just learning. It requires some interpretation. So my conclusion of this is that you have the knowledge of the learning process. That's knowledge. And the knowledge here is understanding. Or better understanding, I should say. And this is a deformation. Okay, so that's the situation for the learning process. Where will I meet this? Well, I will meet it in observed reality, existing reality. I will meet it in existing reality, real reality, if I can say that. The moment reality, the interval reality, the observed reality, the big interval reality. There will be deformations, and they will actually, so this will lead to sort of understanding of the universe. So the existence requires more understanding than the knowing. So I'm not so keen on people say knowledge is fantastic, knowledge is everything we need knowledge. No, we don't need knowledge. Knowledge is in a dictionary. Understanding we need. And that's what I try to tell to students. I say you have to understand it. Don't learn it by heart, understand it, and then you know it, in my opinion. Okay, but this is just kind of on the level of the brain activity, the deformation of a learning process. Then I say this because to me it was a revelation. I did this independent for didactics. And then I discovered that my theory of non-commutative geometry is this. I mean, the non-commutative geometry, my version, has non-idempotent elements. Intersection is not necessarily self. There is a self-intersection which is not driven. I think I said that in the earlier lectures. And so I have over one point in the thing, in the theory, I have several over this point. Let's call it sigma. I have sigma 1, sigma 2, sigma n, which is the aspect that I told you about here, this thing. And what is this? This is the biggest idempotent. This is idempotent, and these are not idempotent. And the largest idempotent in it is that, so they lying over this. So in my non-commutative geometry, I have a kind of blow-up deformation from the idempotent in the Boolean theory to non-idempotence, which so sigma 1 intersection sigma 1. It's in the lattice notation, a meet. It is not sigma 1. But sigma inter sigma is sigma. And so that splits, they are all above this, and that is the aspect deformation of the commutative. So I have a commutative geometry here, and an aspect deformation is the non-commutative geometry. And then to my surprise, when this model for reality, I have another example which I will finish, I think, is time. Yeah, I will finish in one sentence or two sentences. This is the following. I have reality, I have existing reality, and I have observed reality. You can view the existing reality as a sub, but the observed is not a sub, so there is a deformation. And it really fits this thing I did with the learning process. Observation is a learning process. An existing process, we don't think of it as a learning process, but in a sense it is. And it's a deformation in that sense. And I can explain it completely, maybe I will do in a later lecture. This is deformation, and this too. And this is certainly this one, even a rough deformation. So that's the reason that this appears here. And the organic causality will be a deformation of the observed causality in the same sense, in the learning process sense. So this is a kind of philosophical reason why, or rather strange in my opinion, that everything seems to be in this process, in this process version, everything comes from the same structure of deformation of processes. And the deformation goes in the opposite direction of what you would think. You would think that the observation is the deformation of the real thing. But since we talk about the deformation, we do the different. We do it from deformation in that way. Here too. So this is necessary. I did it very quickly. Perhaps I will devote a whole mini section about this later. But this is interesting for us, and the organic case is now what I will do next time. Okay, thank you.